The next speaker is Igor Khavkine, who will talk on q-deformed spin flows for Riemannian polygram.
So first I'd like to thank the organizers for giving me the opportunity to speak here today. So I'm going to be describing some work that was done jointly with Dan Christensen. He described it briefly earlier in his talk. So for anyone who is interested in details, I encourage you to look up our preprint, which was also recently published in Classical and Quantum Gravity. So I'm going to run through the what, why, how, and sort of so what of this work. And this is a little teaser that I'll explain later on. So this was covered already by Carlo Rovelli and by Dan, so I'll run through it very quickly. We work with spin foams, which live in the dual of the triangulation of a four-manifold. So we color two-dimensional faces, or dual faces, or faces because in four dimensions that's equivalent, by spins. A priori it could be anything. And spin foam models, different ones, assign amplitudes to particular spin foams by taking a product of amplitudes of individual dual faces, dual edges, and dual vertices. So we can compute the total partition function, knowing these amplitudes, and expectation values of observables, which are defined on spin foams. So our goal is to compute these things numerically. So this is the Barrett-Crane model, the model that we use. It's a spin foam model for Riemannian general relativity. Historically, it was derived as a constrained version of discretized BF theory. Since then, it's also been derived in other ways, for example, from group field theory. Barrett-Crane has specified the vertex amplitude, as I've showed you, which is used where I've showed you in the previous slide. However, the edge and face amplitudes are left unspecified, and there are several choices for those. So this amplitude is given by the 10J spin network. These four valent vertices are basically invariant tensors between in the space of four tensor product of four copies of balanced representations of spin 4, which is a double cover of SO4, and we can decompose them into in this way in terms of representations of SU2. So let me tell you first about q-deformation. So what is it? If we have, let's do it first for SU2, it's simpler. If we have the Lie group SU2, we can take its Lie algebra and construct the universal equivalency algebra, and briefly can be summarized as the algebra generated by three elements, sigma 1 plus minus sigma 3, which are the following matrices, with the following commutation relations. On the Q side, what happens is we take a similar algebra, so we have different generators and different relations. So what is important to remember is that if Q is taken to 1, which corresponds to the absence of deformation, these relations formally reproduce the commutation relations of the universal equivalency algebra. So to do representation theory, we'll look at E-reps of this algebra. It's well known they're classified by half integers called spins. In the q-deformed case, for generic Q, this is basically the same thing. However, if you take Q to be a primitive root of unity, which is defined by this exponential, and R being a positive integer, so if you take R to, for example, to infinity, you can recover in principle the Q equals 1 limit. We find that the E-reps are cut off at some finite value of J related to this R. So to go to a spin 4, we use the isomorphism of spin 4 as a product of two copies of C2, and write the algebra this way. For q-deformed, we can do the same thing, except now we find we have a two-parameter family of q-deformations, one for each copy of SE2. And I'll tell you about the relation between these two parameters a bit later. On this side, we're dealing with spin networks, which are graphs drawn in a plane, which could have crossings. While on the Q side, what we have to deal with are ribbon graphs, where we have to make the distinction between over and under crossings. So here's some reasons for why we want to look at q-deformation. So one reason is regularization, using this fact that the number of E-reps of the q-deformed algebra is finite. For example, the Ponzano regime that was introduced for 3D Riemannian gravity was found out to be divergent some time ago, and later Thrive and Viro showed that if this model is regularized by using root of unity Q, the expectation value is the partition function and other observables become finite and give you invariance of three manifolds. So Dan mentioned something similar for the DFKR model, which was found numerically. This model was introduced by Dipicci, Friedel, Krasnov, and Rovelli. And we find that at Q, set to a root of unity, this model is regularized, and we've done computations with it. Another important reason to look at q-deformation is the introduction of a cosmological constant. So the argument here is heuristic coming from loop quantum gravity. In loop quantum gravity, we have spin networks which are embedded in a spatial slice, and labeled by, so their graphs are labeled by representation of SE2, which describe quantum spatial geometry. Also, in loop quantum gravity, we can construct certain states called Kodama states, which are parameterized by this number lambda, corresponding to a positive cosmological constant. So this state approximates the de Sitter spacetime, which is a vacuum solution of Einstein equations with a positive cosmological constant. And Smolin has argued that the invariance of this state under large gauge transformations necessitates a discretization of the cosmological constant. So lambda becomes proportional to 1 over r, where again r is a positive integer. And if you consider the expansion of the Kodama state in the spin network basis, you find that these coefficients are simply the evaluations of abstract spin networks, as I've showed you before, which are evaluated at as SUQ2 spin networks, with Q given precisely by the root of unity with the corresponding R. So how we go about doing these simulations? So first we have to formulate the q-deformed Barrett-Crane model. The ingredients to do this have been in literature for some time, so it's a matter of collecting them. For example, which of the possible q-deformations do we use? Yetter showed that if we take the two q-deformation parameters to be inverses of each other, this is what you need to do to recover some invariance properties over the Barrett-Crane vertex. And incidentally, this choice also eliminates the ribbon structure from deformed spin networks, which is nice for us because then we only have to specify the crossing structure and not the ribbon structure. So we have to do this for the 10J symbol only. All other spin networks that come up are planar, so we can just use the crossings don't come up there. And it's not particularly trivial to get the crossing structure, which is basically specified in the Crane-Yetter model, which is a precursor to the Barrett-Crane model. So this is what the crossing structure looks like. We give sort of a concise description of this in our paper, which we hope is clearer than the original reference. So the nice thing about it is that even though it may not appear this way, the evaluation of the spin network still retains symmetry under permutation of the 5 vertices. And the efficient algorithm that Dan and a collaborator have constructed to evaluate the 10J symbol when q is equal to 1 can be extended to the q-deformed case, and we have done this. So to simulate this on the computer, we need to write some software that will be able to evaluate q-deformed spin networks. And so if you want to evaluate some of those, give us a call, and we can help you out. So for example, here's an illustration of, so this is the complex q-plane, and what I'm plotting here are contours of a scaled real part of the tetrahedral spin network where all spins are set to 4. So we can do these computations symbolically, rationally, and also with floating point computations. The unfortunate part is that when q is away from this unit circle, the floating point computations become unstable. But for root of unity q, that's still okay. So we tried to compute these expectation values, even though if we set q to a root of unity, the number of spin foams is finite. The number of spin foams is still very large, so we use statistical methods to evaluate the sums, specifically the Metropolis algorithm. So for this algorithm, you need to specify a certain set of elementary moves that sort of walk in a space of all spin foams and sample it with the appropriate weights. So the moves that we use here correspond to choosing some elementary dual 3-cell or from the triangulation corresponding to the edges of the triangulation, and just taking its two-dimensional surface. So this is and adding to each face or each triangle in that surface 1 or unit of spin or subtracting 1 unit of spin. And this geometric idea of sort of closed bubbles has come up already in the talk by Wade Charrington, and will come up again in the talk by Florian Conradi later this afternoon. So the statistical algorithm works very well because we've already know that in the undeformed case, the amplitudes are positive, but we've also shown that this holds in the root of unity case. So this is very nice. So here are some of the models that we used. As I mentioned, there are several choices for edge and face amplitudes. There's a model proposed by Perez-Rovelli, the DFKR, another model proposed by Bias and Christensen in previous numerical work. So I won't tell you exactly what these quantities are, but I can tell you that both the loop and this I symbol are roughly linear in the parameter j, whether the classical or the q-deformed version. So here are some of the observables that we study. So Dan already mentioned some of these, like average spin per phase or average spin squared per phase with the mean subtracted, average area per phase, and a new observable which induced is the spin correlation function. I'll talk about it a bit more later. So notice that here in the summands I'm using what we're calling quantum half integers instead of regular integers as one might naively expect. So when q is equal to 1, these just correspond to half integers again, but when q is the root of unity with the following parameter r, they behave sinusoidally. So I'll show it to you in a couple of slides. So here are some of our results. So here we're plotting the area. So this is the average area for the Perez-Rovelli model. This is the average spin for the Perez-Rovelli model versus the r parameter, which we try to take to infinity and compare it to the q equals 1 computation, and also the average spin for the Bias-Christensen and the average area for the Bias-Christensen models. And notice here that in some cases we have agreement with the limit, but in some cases we don't. And this is very puzzling, and this is a little bit at odds with the interpretation that the q deformation parameter corresponds to a non-zero cosmological constant, because at least I would expect more continuous behavior than what we see here in that case. So here's an explanation, at least with the way we found it, for why we see this discontinuity. Well, I have to introduce something that I call the single spin distribution. So this is basically the probability of finding any particular spin label if you just consider all faces of all possible spin forms for a given triangulation. So we can estimate these things numerically by just taking histograms during a simulation. And here you see two, so the dots represent this numerical data. The black dots represent the data for the Bias-Christensen model for the q equals 1 case, no deformation. And the white dots, they correspond to root of unity q with r taken to 50, I believe. So notice the big difference. So here at small spins, they basically coincide. But at large spins, while the undeformed case continues to decay, there is a peak at the boundary of the admissible spins in the q-deformed case. So there's a very big difference here. And why does it matter? So the reason this distribution is important is because we can take the summands that I've defined for some of the observables on previous slide and just average them against this distribution to get the expectation value. So if I do this for just the integer j, or this formula for the spin, which I've plotted here, they're sort of close to each other, then this large peak at j close to or r over 2 will dominate. And if you take r to infinity, what you basically have, you just have the value taken from this point on the curve, which will diverge linearly as you take r to infinity. So you won't get any agreement with the undeformed results. If you take, on the other hand, the sort of the q-deformed analogs, then you see that their values go down again close to the limit of the admissible range. So at least we're able to recover some finite limit as we take r to infinity. And so the difference between these two distributions is basically what accounts for the discontinuity in the expectation values as we compare q equals 1 and r goes to infinity limits. So this is basically here. This is what makes a difference. the continuous curves, actually, I'll hide that for it. The continuous curves that you see here are what we call single bubble amplitudes. So I told you before that the elementary moves that we use in constructing spin foams correspond to taking some bubble, closed bubble, and adding adding or subtracting a unit of spin to each face on it. So if we take just the vacuum configuration, which corresponds to the zero representation labeling each face, and then take one elementary bubble and assign the same spin j to each face, and then just compute the amplitude with the product formula that you've seen previously, then we precisely get these continuous curves, which match extremely well to this numerical data. So this suggests that if you actually consider the spin foams that contribute to the summation of the partition function expectation values, it is the spin foams which are full of these isolated bubbles which dominate. So this we find for the Barrett-Christensen model and for the Perez-Rovelli model, which although is not shown here. However, if we look at the DFKR model, this weight is distributed much more differently. And if you look carefully, you notice that the numerical data for the single spin distribution and the theoretical single bubble curves do not agree. So this is a logarithmic axis, and if you plot them non-logarithmically, the difference will be even greater. So for the DFKR model, we can't say anything about the dominance of, well, we can say that the single or isolated bubble spin foams do not actually dominate. And finally, let me tell you about a little bit about the spin correlation function. So I showed you the formula before, but I'll just describe heuristically what it represents. What we do is we take the spin labels assigned to two different faces, a certain distance apart, and see what they are on average. So first, the distance that we use here is a certain combinatorial distance that we get from the triangulation, because there's no sort of physical notion of distance we can use. There's no background metric that we have in our model here. So the normalization of the spin correlation function is such that at zero separation, we'll want it to always be 1. And if you take its value at any sort of finite separation, if it's positive, then it means that on average, we expect the two spins that are separated by this distance to be above the average spin, while if it's negative, or simultaneously above or below the average spin. So they're positively correlated. While if the correlation function is negative, we expect the spins on plaquettes that are separated, or faces that are separated, to be one above and one below. So I'm showing the spin correlation function for two different lattices. So this is the minimal triangulation of the four-sphere that I think Dan has mentioned in his talk. But we've also done calculations on larger triangulations. And this observable is much more interesting on larger ones, because you can take a look at its behavior for larger distances. So let me just concentrate on the larger triangulation. So we find that there's some characteristic dip in the correlation function for Barrett-Christensen and Perez-Rovelli models, and that there's some rise, and looks like there's another dip. So and this behavior may actually continue if we take larger lattices and look at longer distance correlation behavior. So this is somewhat consistent with the dominance of isolated bubble spin foams that I mentioned before, because if you take a spin that sits on one of these bubbles, well, you just by combinatorically you expect that most of the spins that are neighbor it are not going to be on the same bubble, so they're going to have value 0. So here you see negative correlation. So you have some spin which is likely to have value above the average, and then 0 which has to be below the average. So this results in negative correlation. While if you go a bit farther away, you see a positive rise, which shows you how far apart these isolated bubbles should be. So if if you take two faces separated by this distance, they happen to be correlated, which suggests that they are sitting on different isolated bubbles. And so we suspect that if we take the larger triangulation calculations and observe this behavior for larger distances, then we may find some kind of oscillating behavior, which is reminiscent of a behavior of something like the density-density correlation of a dilute gas or a liquid. So this is very interesting, I think, and hasn't been sort of explored before. This last curve, which doesn't agree with the same argument as I've shown you, is the DF-KR model. And this result is also consistent with the fact that isolated bubbles do not dominate in our case. So let me just conclude. We are able now to do computations with q-deformed Barrett-Crane model for modest size calculations, triangulations. Okay. We have observed very interesting discontinuous limiting behavior in the observables that we calculate with it, which, for example, puts the non-trivial Q at odds with the sort of the physical interpretation that corresponds to a positive cosmological constant. So we've tried different models, and we've shown that the behavior for the observables in them can be quite different. So again, this reinforces what has been shown before, is that the variations of the Barrett-Crane model depend very strongly on what choices you pick for the edge and face amplitudes, and not just the tangent symbol for the vertex amplitudes. And so here's some possible directions for future work. Maybe we should probably look at what happens if we take Q, not exactly sitting on the unit circle, so not exactly root of unity, but close to it. I mentioned there's some numerical stability issues with these calculations, but we believe if we take Q still close to 1, the magnitude of Q still close to 1, even though it's not 1, we should be able to do some of these calculations. As I already said, it'd be interesting to look at the behavior of the spin-spin correlation function for larger triangulations. And eventually one has to look at the more physical choice of Lorentzian signature compared to Riemannian signature. So thank you for your attention. Do you have any questions?
Thank you very much. Questions? One question about spin-spin correlations.
Okay.
It's for the version of the Barrett-Crane.
Yeah, so for the three versions that we examined.
Okay, I mean, if you want to Riemann calculation,
yeah.
It would be to compare them with 15J symbol. Have you done
15J symbol?
Yeah.
Or
Yeah, the correlation for the 15J symbol.
so like take a single, like the 15J graph and look at the correlations on it?
What do you expect? By spin correlations or?
I'm not sure. So there are many. So this minimal triangulation has about 20 faces, and I think it has. If you look at the amplitude, it has a product of 6 10J symbols, which are sort of similar to 15J symbols. Yeah. So I'm not sure.
This is a product of 6 10Js.
Yeah. So.
Product of 6 10Js. The foresters have got 6 forces.
Oh, okay.
Yeah. So looking at any one particular one would be like, looking at a particular path and a path integral, and it may not tell you very much, right? So you have to look at sort of the total contribution. So I'm not sure if, I don't know what would happen if you look, if you come up with some way to compute the correlation for a single 10 or 50J symbol. And I'm not sure it's exactly relevant for at least for the Barrett-Crane model.
Further questions?